So, welcome back to the second week, and we will begin with the fourth lecture on statistics. There will be one more tomorrow, and in the afternoon, we'll have the second session of data handling. Both the sessions will have quizzes. So, may I request Arun to continue with his lecture? Thank you.
Okay, thank you, Ritesh. So in the last class, so we discussed already method of maximum likelihood. So I'll just give a maybe brief recap before moving further. So what we discussed last time is that if we have a set of data set, I mean set of events which we call a sample, so we construct a likelihood by making a product of the probability of the probabilities for individual events. Okay, so that's we call likelihood. And then if the likelihood depends, I mean if the PDF depends on some parameter theta, we estimate the theta using the maximum likelihood method. That means we basically what we do is we maximize the likelihood, or we instead of maximizing the likelihood itself, we actually maximize the um, log likelihood. Okay, so that it is easier to do the numerical maximization. Okay, and in practice we actually minimize the negative of the log likelihood. That's a bit easier. Okay, so that's what we do. We gave some examples like exponential distribution, where we maximize the likelihood, where it is possible to maximize the log likelihood uh, analytically, and using the analytic, maximization, you can obtain the estimator, maximum likelihood estimator for its parameter tau, which is just a sample mean. And we also discussed the other properties of these ML estimators. And here was this was the result of a fit on bin likelihood fit to this 100 events, a sample of 100 events, and we obtained the value of the fitted value of the parameter. And then we also discussed similar thing for the Gaussian, and then we discussed various methods for um, estimating its error or the variance. Okay, so there are different methods, like four different methods: analytic or Monte Carlo methods, RCF bounds, and graphical method. And in most cases, I mean, RCF bound or graphical method is being used to obtain the uh, variance. Okay, so this is what we discussed in the last class. So if there is any question, please ask me. Otherwise, I will move to the um, extended maximum likelihood. If there was any questions on this, okay, then I move on to the maximum likelihood, extended maximum likelihood. So far, when we constructed the likelihood function, we basically made the product of the probabilities for individual events. Okay, so this was the likelihood function that we discussed earlier. Okay, this part. Now imagine that if you had observed say 100 events, n events, and we consider that itself as a Poisson random variable. Okay, earlier we considered it as a constant. Okay, and it's a fixed number of events. Now we consider that as a Poisson random variable with some mean mu. Okay. Then if we have that, then we'll also multiply a probability distribution for obtaining that number of events. Okay. So that probability distribution will be a Poisson distribution because we assume it is a Poisson random variable. So to this likelihood function, we have an additional probability distribution corresponding to the obtaining number of events nu given number of events n given its expected value is nu. Okay, so when you do this, then you can also rewrite in this form. So when we construct a likelihood function like this, assuming n is a Poisson random variable, then we call this as extended likelihood function. Okay, and now we can consider two cases where n is either a function of theta, that it is also depends on the parameter theta, or uh, um, nu is an independent parameter, in, is an independent parameter. Okay, doesn't depend on theta. So in the first case, suppose nu is a function of theta, the extended log likelihood function, then you can write this in this form. So now that nu depends on theta, so when you write the log likelihood, you will expand this form, and then there will be constant terms coming from this one. Okay, so at the end, if you ignore the constant term, so it will be of this form. Now you can see that in addition to um, you know log of f of xi, you have additional terms corresponding to the nu, which is a function of theta. Now when you do this maximization of log likelihood to obtain the parameter theta, it will exploit information not only from the distribution of the f of x, but also from the value of this, I mean, new information from the number of events. Okay, so from both the information, from both the informations, it will obtain the value of the theta. That's why it will improve its variances, or may result in smaller variance in obtaining the value of its parameter. Okay, now let's consider the other case when nu doesn't depend on theta, then this is an independent parameter, then we should expect to estimate the mean of the, or expected value of nu should be corresponding to the number of events. Okay, when you maximize it, and theta I would be the same as the previous ML case. However, that means it's basically doing as it was done before. Okay, however, this is still helpful in cases when, say, you have a PDF which is a combination of several components. For example, you can consider, say, signal plus background PDF. So you have a signal PDF and another is background PDF, and you have a total observation of events. Or you have several components of the signal, say 2 components of the signal and background, that kind of cases. So in that case, suppose it is possible that you can write the total PDF as a weighted sum of the individual PDFs. Okay, like in this way, theta I times f of I, where f of I are all known and theta I are all independent. But there is a constant in the form that sum over theta I of individual components should be 1. Okay, and then the if you rewrite the log likelihood function, then it will become in this form. Okay, now you have here as a term nu times theta j. So let's define this term as some mu j. Okay, so if we write this theta j nu to be mu j, then you will have um, here this new term. Here we can add sum over theta j, because this is a times 1 equal to sum over theta j, so we can multiply this here, so that will make up this form. Now if we use this definition of uh, mu, then it will be like sum over mu j plus log of this form. Okay, now you can see that you have this mu j's, which can be considered as the number of signals in your total number of events. Okay, number of signal or number of backgrounds or number of different signals. Or so this, now you can see that these parameters mu are not subject to any constant, unlike the thetas, and n, the total number of events, is sum of independent Poisson variables mu j's with mean mu j's. Okay, and now when you do the maximum likelihood fit, the estimators for mu j can directly gives directly the estimated mean numbers of the number of events of different types, which is can be equivalently can be written as mu j to be theta j hat times n. Okay, now let's take an example to make it clear. Now suppose I take a very simple example, only one signal and one background. Okay, so I have a signal component which is PDF, which is Gaussian, and a background PDF which is exponential. Okay, now suppose I have number of signal events that observed is ns, and number of background events observed is nb, and which is expected to be Poisson distributed with mean mu s and mu b. Okay. Now the PDF can be the total PDF can be written as fraction of signal events times signal PDF plus fraction of background events times background PDF with total number of observed events n to be ns plus nb. Okay. Now when we feed this, we expect to get the estimations for mu s and mu b. Okay. So this is what is shown here. So in this example, say, sorry, I think I missed to write this. I'll correct my slide here. So this should be changed, these numbers here. So um, here I generated an MC sample with mu s 400 and mu b say 1600. So total 2000 events. Okay. And then I performed a extended maximum likelihood fit for both mu s and mu b. Of course, there are other parameters for individual PDFs, like for the exponential, you have the parameter tau, and for the Gaussian, you have the parameter mean and sigma. So those are also estimated along with mu s and mu b. Okay. Now, when you do the fit, you will get this kind of, say, this is the background component here, and this is the signal component here. Okay, in the peak. And when you have more than one parameters, you can also get the covariance matrix that we discussed here, I guess. Let me go back. Yeah, yeah, here. So the covariance matrix would be of this form when you have more than one parameters. Okay, so you can get the individual covariance matrix, and from the covariance matrix, one can get the covariance. This uh, the contour corresponding to the 1 sigma uh, deviation with respect to the fitted value. Okay, so the point here in the left plot, the point here gives the fitted value for the mu s and mu b, and this contour here gives contour of 1 standard deviation. That means when the log likelihood is smaller than the maximum log likelihood by half. Okay, half unit. So, and the tangents in this case, so for example here and here, this gives the 1 sigma deviation for mu s, and the tangents here and here, they give the 1 sigma deviation for mu b. Okay. And similarly, you can also plot the not only the 1 sigma contour but also the 2 sigma contour here. Okay. Now, are there any questions at this point? Seems not. Then, so far, we have discussed the maximum likelihood fit with the unbin dataset, where we simply, um, you know, constructed the likelihood by making a product of the individual probabilities. Okay. Now, suppose we have very large data sample and the number of events are very large, then it is maybe useful to make histograms instead of recording each measurement separately. Okay, so then we have a histogram of number of events expected from, say, some PDF. Now, suppose the number of entries are n1 to nn in n bins, with sum over ni is n total, and say the expected values of number of events in each bin is nu I. Okay, from the expected distributions. So where nu i's can be written in terms of the parameter theta as, say, nu total and total times the iteration within the bin range of this PDF f of x dx. Okay. Now one can think this number of events in each bin ni as a single measurement of, say, n dimensional random vector ni, and then you can construct the joint PDF which of getting, say, ni number of n1 number events of type 1, n2 number of events of type 2, and so on, with the expected numbers nu1, nu2, and so on, as a multinomial distribution, right? So the joint probability in this case will be a multinomial distribution of n1 number of events n1 of type 1, and n2 of type 2, and so on, like this. Okay, with expected numbers such nu1 and nu up to nu n. And here this nu by n total gives the probabilities of getting, say, n1 events of type 1, and so on. Okay, and then when you, so this is again the joint probability is the log likelihood, and then sorry, likelihood. So then if we write the log likelihood function, log of this term, then this will be basically sum over ni times log nu I plus the constant. The constant comes from this. Okay, now in the previous case, in this case we kept the n total to be a um, say constant. Okay, so one thing that I also wanted to mention here, so the term that you see here um, is also you use in as a loss function in your machine learning methods. So can you someone guess what this term is? How does it look like? Okay, so this is also the cross entropy that you use in your machine learning for defining the loss. Okay, now suppose um, we treat the total number of events also as a random variable. Okay, that means n total is not constant, but it is again a random variable with Poisson distribution and with an expected mean to be nu total. Okay, so in that case you will have an um, additional term in the probability distribution as we did in the standard likelihood case. Okay, so that here again this is a Poisson distribution for n total. So when you do this, then if you then simplify this total expression, you will get that this joint probability is simply a product of Poisson distributions for individual beings. So that then you can write in this form. So here you can see that here it is like ni events of type uh, 1 with the expectation nu I, similarly for n such beings. Okay, so this is basically equivalent to treating the number of entries in each bin as an independent Poisson random variable ni with mean nu I. Okay, so then where here the nu I itself, so earlier we defined nu I to be n total times this, in this case nu I to be nu total times the um, integration of the probability density over the bin. Okay, okay, so when we take the log of this likelihood, then there is and drop some constant terms corresponding to n, then you will get the log likelihood which will be of this form, and this is called, again this is the again the extended log likelihood function in the case of bin data set. Okay, now let us see some examples. So we can consider again our previous example with exponential distributions and Gaussian distributions with the same number of 100 measurements. So, and in this case it is binned with um, a binning size of 0.25, and you can see even in this case also the results that you get, the parameters are consistent with what you got from the unbinned likelihood fit. Okay. Now once we do the fit, we also should check whether the fit is good, which we call as good, goodness of fit test. Okay. um, However, in case of maximum likelihood, it doesn't really directly suggest a method of testing the goodness of it. That means if you just take, say, log likelihood or minus 2 log likelihood, that doesn't directly give um, a distribution. I mean, it doesn't have a functional distribution itself. But in some cases, it is possible to obtain the goodness of fit measurement by finding a proper ratio of likelihood functions. Okay. So say for example, say when we did this Poisson distribute this one. Okay. uh, Bin data, assuming the total number of events is also Poisson distributed, so we have Poisson probabilities, product of Poisson probabilities. So in that case, the likelihood that we defined here is L of nu, L of n given nu. Okay. But we can have another likelihood where, which was this one, the numerator only. Now we can have another likelihood which is L of n given n. Okay. And take a ratio of these two. Okay. So when we take the ratio of these two, it will be a joint probability of getting n and vector given nu, uh, over the joint probability of getting n given n. Okay. And when you take this ratio of this likelihood, then some um, some of these terms will cancel out, and what you will get is basically this term. So exponential of n total minus nu total times product of nu I over ni's to the power ni. Okay. And if the hypothesis or the PDF that you consider is correct, and in the large sample limit, this statistic lambda p, if you take the twice negative 2 log lambda p, that behaves like a chi-square distribution. Okay. With n minus m degrees of freedom, where m is the number of parameters, n is the number of events. No, not events. Sorry, number of bins. Okay. So you can use these statistics um, to as a goodness of fit test. And how do we use this? As this is distributed according to a Cascade distribution, we will actually discuss at the end of the least square method, how from the Cascade distribution we obtain whether the fit is good or not. Okay. So that's the end of my likelihood maximum likelihood method. If there are no questions, then I can move to the method of least squares. Are there any questions at this stage? Yeah, go on.
Hello, sir. So, I got the concept of how to apply this maximum likelihood function, but I'm still confused about the meaning behind it. Like, why we go for maximum likelihood thing, and what does it actually mean?
Sorry, I didn't get the point. What did you ask again? Can you repeat? What does
Like,
it mean?
theoretically,
Huh?
theoretically we go for the maximum likelihood function, but why we go for it? Isn't it like likelihood function represent like the data? We try to see the data when we say like our hypothesis of prior is true, but what does it mean by maximizing it?
Okay. So, so imagine this. So what happens is that, suppose you have this data set that we have X, right? So suppose your hypothesis is correct. Okay.
Ji.
And f of x that you consider is correct, then obtaining this data set, the total probability should be the maximum probability, isn't it?
Yes, yes.
So that means if the theta is correct, the value of theta, and theta defines the your probability, right? Probability distribution. So that's the parameter of your distribution or probability distribution that you consider. If theta is the right parameter, okay, so that theta would basically maximize this joint probability of obtaining this data.
Okay.
So if say if the probability if the function is, I mean, if the parameter is that you are choosing is not correct, then getting the probability of getting these events would be small. That probability of getting
So,
xi to xn events would be small, right? Because you are not choosing the probability correctly. I mean, uh, if your probability assumed probability is not correct, then obtaining the data, this data would not be, the probability of getting this data would not be high.
so sir, in case of
So
multiple
suppose I,
variables,
just
yeah,
take, maybe give an example. Suppose I say, let me take this example here. Okay, suppose I have a um, my tau is say 1. Okay, and
G,
I so if my tau is 1, I expect to get this kind of data, right? This is what I
G, G,
expect. Okay, now suppose I choose my tau to be um, you know 2. Okay, the probability of getting this data will be very small. I will get different distribution of data.
G.
So that means the parameter which maximizes this probability, total probability, is the parameter value this one. So if I have
But
say,
in this case, we are changing the value of only one parameter. In case we have multiple parameters like theta 1,
yes,
theta 2, and so on, we can go for
yes,
the maximum likelihood to see which is giving the maximum probability.
yes. So for example, I take two parameter case, say Gaussian. So Gaussian has two parameter, right? So mean and the sigma. So now suppose I have in this case my data matches with the mean of 5 and sigma of 2. Okay, now suppose I consider sigma to be 4, then I expect to get data which is much broader, isn't it? Distribution would be much broader than the one that I have here. Okay, so if I consider a probability distribution with mean 5 and sigma to be say 4, that will not give you the maximum probability to obtain the data that I have now in this plot. Isn't it that so? I mean, isn't it the case?
If-
So that means
Yeah,
the parameter which maximizes the total probability to get this distribution is the correct parameter or the most likely
oh,
parameter.
okay, sir, got it. Thank you.
So the most likely parameter is the one that gives you the maximum probability to get this distribution of data. Is it understood?
Yes, sir, yes, sir.
Okay. Any
There
other question?
is there is another question in the chat, how it is implemented in applying confidence limit at 90% on dark
Ah,
matter exclusion limit.
okay. So that thing will come in the main school. Okay. So that will the confidence estimating the confidence intervals and the exclusion limits will be taught in the main school. So I guess you have to bit wait. Okay, so if there are no further questions, then I can move on to the method of least square. So the other method that is also used to estimate the parameter is called method of least square. So Now let's assume again similar thing. Say suppose you have these points or measurements, say yh, which are some function of say xh, okay, some variable xh, and it has some measurement error, okay, some sigma I, right? Now suppose we consider that each of these yi, um, its mean value, it is distributed um, with some Gaussian distribution, okay, yi is distributed Gaussian, but we do not know what is the actual mean of this yi's, which is expected to be some lambda I, which is unknown, and it is the known variance sigma square, which corresponds to its error that is given in this um, you know measurements. The error is known for the Gaussian distribution, but the mean of this Gaussian is not known. Okay, so that means this yi will be can be distributed in this along this line. Okay, as a Gaussian distribution. Okay, with some mean lambda I, and the sigma which is equal to the error bar given here. Okay, so now we can consider this yh as a single measurement of say n dimensional random vector. Okay, each of these having a Gaussian distribution. So in that case, we can write a joint probability, which is probability of obtaining say y1 to up to yn, and given the mean as lambda I, lambda 1 to lambda n, which are unknown, and the variances sigma 1 square to sigma n square, which are known, which are equal to their errors. Okay, a square of their errors here. But the lambda i's are not known. That means the exact mean of this distribution is not known. That's what we want to find. Now, this joint probability will be simply the product of the Gaussian distributions, a Gaussian PDF. Okay, so which we can write in this form. Okay, where yi are the measured values and lambda I are the expected mean value of the Gaussian, and sigma I are the sigma I squares are their variances. Okay, now suppose this lambda i's independent values are as a function of x, okay, with some parameter theta. So we can write lambda as a function of lambda of x given some parameter theta, and our aim is to estimate these parameters theta. Okay, this can be one parameter or more than one parameters, a vector of parameters. Now we can write, to estimate this, what we have to do if we use the maximum likelihood case is to maximize this log likelihood function for this log likelihood of this joint probability, log of the joint probability, which is log likelihood. So if we write this log likelihood, then you will have sorry log of sum of the log of this term plus sum of the log of this term, and since sigma is are all known, so this is going to be giving some constant, so we drop the this constant terms here, and we kept only the ones which depends on the theta. So this is this term here, which is sum over uh, yi minus lambda square by sigma I square. Okay, now maximizing this, as we say, as I also said earlier, is equivalent to minimizing this term. Okay, or you define a chi-square of theta, which is minus 2 log likelihood, and maximizing log L theta would be equal to minimizing the chi-square, which will give you the same theta. So now this definition is basically nothing but your least square, sum of your least squares, or sum of the residuals. Okay, square of the residuals. and this is the basis for method of least square. And even if yi's are not Gaussian, as long as they are independent, this method is also used to estimate the parameter theta. Okay, but when yi's are Gaussian, they match exactly to maximum likelihood method. And the parameters here that minimize the chi-square are called the least square estimators, theta hat, and the resulting minimum chi-square follows under certain circumstances, which um, we'll discuss later. It follows the chi-square distribution, and the chi-square distribution we discussed 2 classes before, the probability distribution of chi-square function. Okay, now this is for the case when all the YH are independent. Okay, independent measurements. But suppose YH are not independent, that means their covariance matrix sigma I are not sigma I squares are not, I mean this covariance matrix is not diagonal. In that case, one can describe all the YH in as a n-dimensional Gaussian PDF with known variance, known covariance matrix P. So then one can write the log likelihood as the log likelihood of the joint PDF. Okay, which can be written in this form. Okay, where you have yi minus lambda times inverse of the covariance matrix times yj minus lambda. And then if you redefine this as chi-square, so this will be chi-square equal to sum of this term excluding this part. Okay, so this will reduce to the previous expression, this if inverse of this is v is diagonal, then you will get v inverse would be 1 over sigma I squares. Okay, so this is the definition for the chi-square function. Now consider some special case. Now suppose lambda is a linear function of theta. That means we can write lambda as some aj times aj of x times theta. So aj is any linear independent function of linearly independent function of x, and theta j are the parameters. So in this case, um, you can estimate. I mean, you can find the estimators and their variances analytically, and the estimators have zero bias and also minimum variance. So if you write for individual xi's, that means at individual points here, then you can write this like this. Lambda of xi would be of this form, which can be written in terms of matrix form. If you consider aj xi as aij, so it can be written as aij theta j. And then in matrix notation, you can write the chi-square as y minus lambda transport times v inverse y minus lambda. Okay, and lambda can be written as a times theta. A is the matrix. Okay, now given this, if you minimize the chi-square with respect to theta and then set it to 0, then this will be of, you will get an equation of this form. And if this is not singular, you invert it and then you get theta hat, which will be of this form times y, which you can write as simply some, say, set of linear equations. Okay, so theta hats, theta i's will be some bij yj kind of thing. Okay, so you'll get a set of linear equations for this thetas. So when you do this, we have discussed earlier that if we can write this form in this form, then if we have a covariance matrix for y, we can also get the covariance matrix for theta. So which we can do this. So suppose uij are the covariance um, um, terms for the theta ij's, then you can write uij as b transpose, which if you do this simple algebra, you will get of this form, and this is nothing but as equivalently you can write this will be of this form, which you can get from here if you simply do the derivative with respect to theta here. Okay, so you will get of this form, and so covariance terms of theta I theta j, inverse of this covariance terms would be simply half of second derivative of chi square with respect to theta I theta j evaluated at theta hat. Okay, and this, as you can see, that this coincides with the RCF bound when YH are Gaussian distributed. So when YH are Gaussian distributed, chi square corresponds to minus 2 ln log L, and then this will convert, this will become coincide to the RCF bound. And then to use it in a graphical way, we can actually expand chi-square around the value of the chi-square where it is theta equal theta hat. So then you can write in this form. The first derivative here will be 0 because that's the first derivative becomes 0 because you are minimizing the chi-square with respect to theta hat, with respect to theta to get the theta hat. So at theta equal theta hat, the first derivative is 0, and then the only the second derivative is remaining here. And then you can see in this form. Now suppose this is again, you see what we discussed in the maximum likelihood case. If theta I is changes by theta I hat plus sigma theta, then the chi-square here will be changed by chi-square at theta hat plus 1. So when, if you if you replace theta I to be theta I hat plus minus sigma I, then chi-square theta will become chi-square theta hat plus 1. Okay, so that means to get the error in a graphical way, you can scan the parameter around the value around its fitted value to get the distribution of the chi-square as a function of theta, and then get where the chi-square increases from the chi-square mean by 1. So that gives you the 1 sigma error corresponding to the for this parameter theta. Okay, so one can also get the 2D contour if we have more than one parameter, similar to the maximum likelihood case. So here is an example. So I considered one, say, a set of points, say 5 points here with some errors. Okay, and then fitted them with 3 different functions: polynomial of order 0, order 1, which is straight line, and order 2. Okay, then you can see the fitted curves. So of course the constant would not fit. Okay, so the chi-square that you get is very high. Minimum value of the chi-square is quite high. Then you have the straight line here, which gives you the chi-square equal to 3, and this is total chi-square. It's not chi-square per degree of freedom, that we'll discuss later. And for the polynomial of second order, you have this chi-square equal to 2. Can someone say, if I fit a uh, first order polynomial which is straight line, so I have 2 parameters and I have 5 points, how many degrees of freedom are there in the fit? Okay, so the number of degrees of freedom that you get in your fit is number of data points minus the number of parameters. Okay, so that means the number of degrees of freedom for a straight line fit in this case would be 3, and for, I don't know if somebody start writing. No, okay. And the number of parameters, a number of degrees of freedom for the uh, second order polynomial would be 2. Okay. And then you can, for the first order polynomial, which is for the straight line, I also make a plot of chi-square over the parameter slope. Okay, keeping the other parameter to its fitted value. Then you can see the distribution of the, I mean, the chi-square curve. Okay, as a function of this parameter, and you can see it is nicely parabola, and the value of the parameter where the chi-square increases from its minimum value by 1, so that gives the 1 sigma, you know uh, or 1 standard deviation, or 1 sigma error. So that corresponds to, in this case, is of this number value here. Okay. So this is, so far we discussed the core fitting. Now we can discuss again the similar thing, as similar to the likelihood method. We can also discuss the least square fit for bin data. That means if you want to fit an histogram with a least square method to some function, in that case you can define again the yi's are the number of entries in the bin I, and f of x is the your hypothesized PDF. Then the number of entries in each bin lambda I, which is expected value of entries in each bin lambda I, which is expected to be the mean of the YH. Then you can write lambda I to be n is the number of total events times the integration of probability density within the bin range. So that can give you like n times pi theta. Pi is the probability of an event to enter that particular bin. Then the chi-square function becomes, again, you can see the residuals yi minus lambda I square over sigma I square, and sigma is, in this case, are the variances of the number of entries in bin I. Okay, so that variance, if we treat, say, uh, number of events in each bin is Poisson distributed, then the variances will be equal to the mean. So we can replace the variance by its um, mean lambda I, which will write again like n times pi theta. Or alternatively, so if this is the usually we use, but alternatively, if this is more computing, it takes more computing time, then one can approximate sigma square as just simply the number of events that entered into the bin. That means you are using the number of actual entries observed instead of the predicted one. So then you can also write in the denominator yi, in the denominator it's yi instead of lambda I. So that it's called modified least square method. Okay, so this has some advantage, of course, also disadvantage. That advantage will be that it will be computationally easier because yi doesn't depend on theta, but the errors on theta may be poorly estimated, or chi-square may be undefined in some cases. Okay, so here is again the same example that I gave earlier in the maximum likelihood case for the same 100 number events, same histogram, but instead of the using the maximum likelihood fit, use the least square fit to fit this data, and the value of the parameter that you obtained here is compatible with what we got in the maximum likelihood case. Now, once we have the fit, we can perform the goodness of fit test. Okay, and again here, uh, as we already discussed, that this difference yi minus lambda I over sigma I is a measure of the deviation between yi and the and the function lambda I. So the chi-square is basically a total measure of total agreement between observed data and the hypothesis. Okay. Now, if yi are independent Gaussian random variable with say known variances, that is, or if it is not independent, then it should be described by n-dimensional Gaussian with known covariance matrix. And if the hypothesis lambda is linear in theta j and the functional form of the hypothesis is correct, that means your assumed function is correct, then the chi-square mean is distributed according to the chi-square distribution with n minus m degrees of freedom, where n is the number of bins and m is the um, number of parameters. Okay, or if it's on bin likelihood fit, then this n will be basically the number of data points. So we know that the we know the distribution of the chi-square function. So in that case, for a chi-square distribution, the mean value of z, which is z is defined as this. Okay, sorry, z is defined as the chi-square. The mean value of z is equal to the number of degrees of freedom. So if we obtain some chi-square value, then if we can compute the chi-square per number of degrees of freedom. So that will give us a measure of the goodness of fit. So if chi-square by number of degrees of freedom, since this is expected to be mean value of chi-square expected to be number of degrees of freedom, so it's we expect this should be equal to 1. This ratio should be equal to 1. So that means if we get this ratio approximately 1, close to 1, that means fit is good. If it is much less than 1, fit is too good, but we should check if the errors are overestimated or some or correlated, which we did not take into account. Okay, and on the other hand, if this ratio is much larger than 1, much greater than 1, then we have to decide whether the hypothesis is is correct or not, whether this hypothesis can be rejected based on the p-value. So here you can see how do we compute the p-value. Suppose you have number of degrees of freedom is 5, then we expect the distribution of the chi-square will be like this. Okay, and suppose we got a observed chi-square is 10, then we can calculate the p-value, which would be like the probability of having chi-square observed or above that. That means the region um, below this function, the area under this curve above the observed value. Okay, so that gives you the p-value, and based on this p-value, you can see whether you want to reject or accept this fit.
Arun, can you elaborate on the second bullet point, which says that should check whether the errors are overestimated or correlated? You mean that if the errors are overestimated, then chi-square will be small. I suppose that's what you mean.
Yeah, if the errors are
And
overestimated, the
hence,
chi-square could be too good because any function can
yeah,
actually
can
fit
then
it too
fit
good.
it too.
Yeah.
But what about the correlated? Because you mean positively correlated and not negatively correlated, or is it for both? Because if it's positively correlated, then the total error matrix, the total term will be larger.
Yeah,
So how this is?
this will, yeah, if it
Mhm.
is positively correlated. If negatively
Uh-huh.
correlated, maybe
Then
we
errors
may
will be
get
smaller.
yeah,
The
it might
total.
be oppositely opposite effect. Yes.
Okay. 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 Thanks.
Yeah. So yeah, so this is what the case. But if you say in true sense, if you have 10, for example, now you can think like this is here the number of degrees of freedom is n equal to 5. So the mean is for this particular picture here, the mean would be 5. for this distribution, and the variance of chi-square distribution is twice 2n, or two times number of degrees of freedom. So that means variance is 10. So sigma is standard deviation is square root of 2n, which will be square root of 10. So this here, in this case, the 10 would be, say, within 2 standard deviation from the mean. So but you have to think for what you should accept or not. But I don't know if there is a clear recommendation what to accept and what to not.
There is a question I did not
Uh,
understand. The chi-square by NDF is equal to 1 part clearly. Or is it considered to be a good fit?
yeah, okay. So chi-square, the chi-square distribution, right? We discussed earlier. Maybe I should let me stop this slide. I open the other one because I could have kept the function here. Go to
Hi,
that
Arun.
function. Yeah, just let me come back to this.
Yeah.
I'm trying to answer this question. Open the chi-square distribution function here. Yeah. Okay, can you see my slide? Okay, so here, this is the chi-square distribution. So what we discussed here, so the chi-square function is defined like this. Okay, so this was discussed 2 days before, yeah, 2 classes before. So we have this chi-square where the z is basically defined as this, which you defined the chi-square in our least square fit, right? Exactly this one, where mu I was the lambda I in our definition. Now, if we obtain some value of the chi-square, minimum chi-square, this value, if that is a random variable, because that is a function of random variables xi, as yeah, yh, since yh are random variables, so the chi-square itself will also be a random variable, or the estimator itself will be a random variable, right? So in that case, the chi-square will be for that particular that number of degrees of freedom that we have in our fit would be distributed according to this chi-square distribution, according to this function. So we expect for that number of degrees of freedom, we will have a distribution of the chi-square if we define the chi-square to be like this. Okay. Now, from our after our fit, we got a minimum value of the chi-square, and this falls somewhere. Okay, we'll get some number. Now, if we have n for if we have when we have fit, like say I had that 5 points with say linear straight line fit. In that case, I said if I have 5 points and straight line has 2 parameters, the number of degrees of freedom is 3, right? So for number of degrees of freedom 3, we will have a distribution for the chi-square function. Okay. Now we know that from this distribution, the mean of the variable chi-square is n, and the variance of the chi-square is twice the n, where n is the number of degrees of freedom. So if we have, say, number of degrees of freedom is 3, so that means the mean of this distribution would be 3, and the variance will be 6. Okay, for that distribution. Now, if we have if we obtained a minimum chi-square, if that for number of degrees of freedom 3, if we got the value of the minimum chi-square to be around 3, that means the chi-square for number of degrees of freedom would be around 1, which is expected, because that means the chi-square mean that we got is close to the mean of the our distribution, expected distribution. Okay, that means our fit is good. We are getting close to its mean of the chi-square. But if we got far away from the mean, then we have to see whether this is acceptable, because the probability of getting some number from a distribution very far from its mean is small, right? So for this distribution, getting a value here, the probability is small compared to getting a value here close to its mean. So that's why if we have a chi-square mean that we got for degrees of freedom close to 1. That means this is a good fit. Okay. Any other questions?
There is a question.
When
Arun, can you please?
chi-square, yeah, chi-square per number of degrees of freedom for a fit in root, it shows a very large number corresponds to 1, even though it's a seemingly, no, this, when you say seemingly good fit, I do not know how do you mean by seemingly good fit. So if you are comparing it through I, um, maybe the function is not correct function that you are fitting, or I mean it's not, it doesn't describe the data correctly. Otherwise, you would expect to get close to 1. If it is, say, a cache curve per number digit term, which is 2, 3, 4, like this, that means you are basically few sigma away from its mean, right? Because the sigma is square root of 2n. Okay.
You can also share one such example which you are referring to, that it's seemingly a good fit.
Yeah, that
You
would be
can
good.
share with us and
Yeah.
then we can see.
Okay. So, any other question? Okay. If not, I think my part is over. So I think that's what I wanted to cover. So tomorrow I will not have any other lecture, I guess, because I guess we will have tutorials continuing.
Only if, things are not clear. So I guess it was tutorial from day one that people wanted me to cover, that I can do. But okay, at the end of the
Yeah, end
tutorial
of
today, we
today
can see.
we'll discuss. Yes.
I think Ritesh needs to conduct the quiz. There is a question in the meantime. Could you please explain the degrees of freedom once again?
Degrees of freedom. So degrees of freedom is, as I, where was that? Uh, here. Okay. So the degrees of freedom is, um, when you have, say, here you have um, 5 points, right? Or five, yeah, 5 measurements. Okay. So in this case, there are 5 measurements, and you are fitting a parameter, fitting a function with 2 parameters. Okay. So the remaining, you know, degrees of freedom, the number of degrees of freedom that you calculate is basically um, uh, number of measurements minus the number of parameters. Okay. So that gives you the number of degrees of freedom.
So, for example, if you're fitting, there 2 points are there, just adding to it. Just to illustrate one more thing, if you have
Yeah.
2 points, you will always fit a straight line to it. So the number of degrees of freedom is zero there.
So is it good to have higher degrees of freedom or less? I mean, if the number of observed number of points are more, then the degrees of freedom will be higher because the
Yeah.
fit parameters
So
will
for
know them.
example, so how do you, so for example, if I have 3 points, 3 measurements, so 3 points, what is the function that, um, I mean, if you say fit,
If
You
we
can
fit a
fit
straight line, there
that
will be
line,
two
it's okay,
parameters.
two parameters. But if you say fit the second order polynomial for three measurements, then in that case it will perfectly fit that that points, because you can you have three measurements and three parameters. Okay, so then the function that will perfectly fit this, so you will have no additional degrees of freedom.
Okay.
What if we have more number of free parameters and less number of data points? Is the fit well defined?
Now if you have more number of parameters or less number of measurements, can you get that parameters, because the number of equations
Yeah,
uh, that you need, uh,
great words.
It's
I'm not sure.
it's always a good idea to choose. So, for example, if you have five number of data points and you use 10 degrees of polynomial, it will always fit it. So, it's not a good idea to choose that fit function.
Now if you have five measurements, the polynomial with order 5 will fit it perfectly.
Yeah, I was saying that with 10 parameters, you should not fit it. Maybe go with start with start with one, then two, then three, no, and see if it is improving further or not. Always start with low number of uh, parameters in the function.
Okay. So, sh- just give me a hint. When should we start the quiz?
Yeah, I think we can start probably. I was thinking how to explain it a bit better, this number degrees of freedom.
Okay.
So suppose we have a linear equations. Um, then if we have n equations, then you can maximally obtain n parameters, right? N unknowns. Or can you do more than that? I don't know. I mean, I do not
Sorry,
know.
Arun, what's the question? What are you saying?
So suppose you have n linear equations, n set of linear equations.
Uh-huh.
So, and can you do more than n number of unknown parameters? Estimate more number of unknown parameters from that. So
You
n
can't
n
you can't estimate more than n, but you can find the region in whatever m larger than n dimensional space, which is consistent with this equation. So you can have one equation in three dimension. You'll end up having two-dimensional plane that satisfies uh, this thing. If you have two equation in three dimension, you will have a line, one parameter line which will satisfy this equation. So it
Um,
constrains a lot, but still there is a lot of freedom.
but isn't like if we have just three parameters, let's say three data points, and if we start fitting with, let's say, five parameter polynomial will most probably describe three data points very well.
Yeah,
Uh,
in fact,
so
that
we
I
should,
forgot what's
yeah.
called Lagrange polynomial and whatever it is called. If you have n points, you can fit nth degree polynomial which exactly passes through that.
Yeah, that's what I was saying. So if we
Yeah,
have say these 5 points, in this case, if you consider the polynomial 4, which has 5 parameters, it will
yeah,
exactly pass through that point.
yeah.
So any additional parameter will not have any value.
And then
Uh,
it is, sorry,
yeah,
I
yeah,
was
yeah.
just, mhm. Sorry, go ahead, Ritesh.
No, no, continue. Nothing. That's exactly I wanted to repeat.
I was just saying that, and we should always, there is a procedure, like we should always start with lower number of degrees, sorry, lower number of parameters in the function compared to the fit and see if adding another parameter helps you or not. For example, you know that if you know that your back, let's say some shape is described by polynomial, but whether it's polynomial of order 1, 2, 3, that you should always start with the lowest order and then see if you gain anything when you move to uh,
Yeah,
polynomial of order 2 or polynomial of order 3, and how to see whether you have gained or not. There are various ways you can see, and we can discuss this later also.
yeah. So basically, what I would say that any kind of fitting is like a data compression. So you have five real number. If you can describe this five real number in using less than five real number, then you have a fit. Otherwise, it's just parameter, right? So
Yeah.
if you are using fourth degree, as Arun was saying, then you can exactly make that curve pass through these five points. So you are not fitting. I mean, that's not called the fit. Fit means that you are not doing data compression. You have to have less than five real number to describe five real, right? So you should stop at maximum third degree, which will have four parameters. And that I can say that knowing 4 points, I can predict the fifth point. If you can't do that, then there's no information compression. It is not a model. It's not a fit. I mean, technically it's a fit, but it's just a mathematical exercise. It's useless. That's all from my side.
Yeah, thanks, Ritesh.
So, so let's
I think I think we can.
begin the quiz. Okay, and the quiz will be exactly 5 minutes. I'll just send the link. Set it. So your link is here. It's on, and you can already start looking at it. The link is in the chat box. And after the quiz, we'll take few minutes break. We just say 11:25. We start the lecture, the tutorial session. 11:25.
In the meantime, Arun, I think students will need the link to your slides, and there is, in fact, someone has asked if you can please share the link for this parameter slide.
Which slide?
Parameter, what we did today.
Okay, yeah, okay. So today's slides.
Yeah.
Yeah. Yeah, Arun said he will send the link and then I will upload it.
Okay.
I will send the, I mean, he can share on the chat box.
I just sent in the chat box.
Okay. Those who already submitted can take few minutes break. We are back at 11:25. Still 1.5 minutes to go for the quiz to finish. It's a short quiz. You can finish much quicker than 5 minutes.
Somebody want again the to say reshare the quiz link.
Some people did not get. Okay, so quiz time is over. I'm gonna close the quiz in 10 seconds. So please submit it.
Pritish, there is a question for you. Can you please explain about how n-dimensional space can be described with m parameters? Can you share the same example?
Okay, just let me do this thing. Close it. Yeah, okay. So think in terms of, let's say, two-dimensional space, that is your n-dimensional space. Okay, and you have one observation. N-dimensional space means that n is the number of free parameters, and m equal to 1 means you have one data point. Okay, so that means I can, and if there's one equation of two variables giving me a number, so there could be, if it is a linear equation, okay, then there is a line. This is the equation of a line. Okay, so I can always produce the exact same data for any point on those two lines, two-dimensional space, that line on the two-dimensional space. Okay, but suppose in the same case I have two data. So each data point is one line, two data point is two lines that will cross at some point. That point uniquely describes both the data. Okay. Now suppose you have three data points. Now 3 points need not cross at the same time. Okay, three lines. So third data point will cross each of the other line at some point. But if there are self-consistency is there is the same theory behind all three data points, then those all three crossings will be nearby. Okay. Now idea is what is the value of parameter I should take that will best describe all these three data, and that's the method of likelihood. Okay, so if you have less number of data than the number of parameters, okay, then you have exact solutions. And no, I say exact solution is the solution space could be not one point, could be larger than a large number of parameter configuration can give you the data exactly. And where your number of data points is larger than the number of parameters, okay, then you will have to have a tussle between any subset will give you one unique solution. Okay. So if you combine all the data points, then you have to say you have to minimize the deviation of all the data points from the proposed point, and that's the maximum likelihood does. That's what we say that this point represents the fitting in the free parameters. Those that value of free parameters explains the data, all the data, in the best possible way. Because whatever this parameter point predicts, the actual data deviation from this is the minimum. The minimum deviation, that is chi-square, being minimized or the likelihood being maximized. So that's Vitali's questions answered. So next is Swasti Rathore. Regarding the chi-square doubt, I possibly do not understand this parameter in root well. Here is one of the histogram with Gaussian fit and chi-square for immediate nuclear. So let me have a look.
So yes, I looked at the fit. Visually, it looks good, but then somewhere the chi-square is coming higher. So did you see in the log plot, are there any bins in the tails which are not explained well by this Gaussian fit? So just look at the log plot and also plot data minus fit over fit. That will also tell you in which bins you have very much deviated fit. So if these two things you can do, I think you will understand this better. But I agree with you visually, the way you have presented just this plot, it seems like a reasonable fit, and chi-square is seems to be quite high for this good fit. So just look at the tails. I'm sure it's coming from the tails, and also look at data minus fit over fit. And there is one more parameter called p-value, which gives the probability of obtaining this chi-square with that number of degrees of freedom. Also have a look at that.
Okay, so I guess uh, Shilpi can take over from here. We can start our session.
Okay, so I'll first share the exercises, the Google Doc with you. Just a second. So today's exercise, here we will learn two things. First, we will do the bind fit um, with one parameter, and then the second exercise is unbind fit with two parameters. And we are not just going to do fitting, but we are going to apply whatever we learned in the past few days to make a few cross checks. So first, let's go to the first question. So this question, let me just share my screen. Sorry, it's taking me a while to share because the app got updated. So, so the first exercise is the following, and that is you have to generate exponentially distributed random variables, around 5,000 exponentially distributed random variables with the decay parameter tau equals to 5, meaning a random variable which follows this distribution. Sorry, x by tau. Okay. Now, then you bin it. So you have 5,000 random variables. You bin it. Then the task is to perform a bin likelihood fit, meaning once you have this, you know the truth value of tau parameter, but the task is to, if you're given these binned values, you have to write the likelihood function by hand, pass it on to Minui, and then see what Minui gives as the best fitted parameter. So let's say it gives you, it will not give you exactly 5, but it will give you maybe 4.8 or 4.7, whatever it gives. So you have to provide log likelihood function by hand to Minui. That's the first task. Okay, I'll first explain what the exercise is about, and then I'll go one by to each of the points. Then the second part of this exercise is to uh, loop over. So in this exercise, in this first part, you used Minui to give you the best fitted parameter value and the uncertainty on this. Okay, provided given that you provided the log likelihood function that you constructed by hand. Now the next part of this exercise is not to use Minui, but just loop over various values of tau parameter. Let's say I know that my tau is 5, so maybe I loop from tau start equals 4 to tau equals 6, and I'll take a step size of zero point 0.1, and then I will loop over these tau parameters. Every time I will calculate log likelihood for corresponding to each tau parameter that I am looping over, and then I will plot minus 2 log L as a function of the tau parameter. You have to see what kind of function you get, what kind of shape you get. Okay. Then from this shape, you can learn a lot. That we learned today and also on Friday that the minimum value of this minus 2 log L corresponds to the best fitted value. So you can then compare this best fit value with the one that you got from Minui. Then the second, you can also estimate the uncertainty. The last day you learned that if you go zero point 0.5 in each direction, that gives you 1 sigma uncertainty. Meaning if you go to increase minus 2 log L by zero point 0.5 in both the directions, then you get the uncertainty. So you have to compare this uncertainty with the uncertainty that you got here. Okay, this is the second part of the exercise. So at least are these 2 points clear to everyone? Or you want me to repeat?
Not ask two
Sorry,
conflicting questions.
sorry, just
He
a
just
second.
means what? So, if somebody has question, please raise your hand and ask the question.
Okay, so I guess these 2 points are clear to everyone. Then the third part of this exercise is to yeah. Last day you learned that uh, the unbiased estimator and the maximum likelihood estimator of an exponential function, of the parameter of the exponential function, is its sample mean. So if you have sample mean, and in fact we had an exercise related to it last time on Friday. So if you have 5,000 measurements, then you can take a sample mean of it, or tau hat, of all these measurements. Okay, then you can compare this thing with this thing, and then with Minui, what you get with Minui. And then the uncertainty on this tau hat parameter, meaning sample mean. Remember how it is, how does it go? Its variance is given as sigma square by n. Since you don't know the sigma, where sigma is the population, standard deviation of the population, you don't know, so you can construct it from the sample. You can take the sample variance here. Okay, and sample variance is xi minus xi bar whole square by 1 by n minus 1. So that's how you can. So if you can compare these three things, I think that will be a good exercise, and you will learn from here how to construct likelihood by hand, and how to use this kind of distribution to get at the best fitted value of the parameter, and how to code the uncertainty. In fact, this is what Minui does. And then how does the sample mean compare with the two other ways. There is one more thing that you can do to code the uncertainty, and that is fourth way of coding uncertainty. First way was from Minui. Second way was the graphical method, which always works. Third way is coding this uncertainty on sample mean. And the fourth way is Monte Carlo trials. So in Monte Carlo trials, you perform, let's say, 1,000 experiments. And in each experiment, you throw 5,000 random variables which are exponentially distributed. Then you do a maximum likelihood fit, maybe by passing to Minui. That's completely fine. And then you get the fitted parameter tau. Just look at the distribution. So whatever fitted parameter tau hat that you get, you put it in the histogram. Then you go to another Monte Carlo experiment, again throw 5,000 random variables, again do maximum likelihood fit, get the tau hat, again put that in a histogram. So you will get the distribution of tau hat something like this, and it's sigma. You should confirm for yourself if it is Gaussian or not. And then the sigma is another way of quoting uncertainty, if you remember from Arun's lecture last week, Friday. So is the whole exercise clear to you? Because then I'll go on explaining how to construct the likelihood. People can also raise their hands. Okay, perfect then.
There are questions. Some people have raised their hands.
No, they're not questions. I asked them to raise their hands. Okay. Okay, so now let's go to the first part of this exercise, how to construct the likelihood. So I'll just give you hints. You have to do it yourself, and I'll share a partial code. So when you have binned the data, so first of all, what you learned today is that the likelihood function is given measurements xi's. You are trying to fit for parameter theta, and the way you do is that the joint PDF, or the joint PDF, meaning multiplication of the probabilities, individual probabilities of getting each xi, that has to be maximized. Okay, that's what we learned. Now for a bint distribution, what you want to do is you want to you want to maximize the probability of getting these many events in this bin, these many events in this bin, which means number of events. I'll just do log L actually, so that it becomes sum over this thing. It's easier. Okay. So that the sum over the uh, probability of getting ni events in ith bin is maximized. Okay, that is what we are trying to do. Now, the probability, what's the, for that you need to know what kind of probability distribution does each bin follow, number of events in each bin follow. It's the number of events. So can someone tell me what kind of, so let's say if I'm considering this bin, what kind of probability distribution will it follow? Anyone? Exactly, Poisson. So, so how do we write the, for ith bin, how do we write the Poisson distribution? E to the power minus lambda, ith bin, lambda to the power k is the number of events in ith bin, by ki factorial. Let's say I'll remove I just for simplicity, because then you can just multiply. Okay. This is the actually it's log here. So I'll take the log of this minus lambda plus k log lambda minus log k factorial. Now what is lambda? Lambda is the expectation in that bin, and k is your observation, meaning you observed k number of events. For example, if you got let's say 10 here, so k will be 10. Okay. Now the question is, what is lambda? How do we estimate lambda now? So what is your expectation in that bin? You know that it's following exponential distribution, because this is what you're trying to fit. So if this is if this is following exponential distribution, then how will you calculate the expectation in this bin, let's say? Let me draw it again in a zoomed version. I'm just zooming in one of the bins. So how will you calculate the expectation from this from this exponential in this bin? So what will you do? You will first of all, let's see what do you expect at this time interval, at this point of time, which is sort of the midpoint of this bin. You expect uh, you will expect 1 over tau e to the power minus ti by tau, right? That's what you expect, the fraction of events in that bin. And if your total number of events in this complete histogram is n, then the total number of events in that bin will be multiplied by n. Okay. But it's the expectation at this point. We want the total number of events in this complete bin. So what we make one assumption that the exponential is not varying too much in this bin, so that I just assume that whatever expectation I have at this point is just can be used to uh, can be used at all the time points in this bin. So it becomes times bin width. Is this point clear? How to get the lambda value? Can people ask question if it's not clear, or can say if it's clear? Okay. Okay. Thanks. But anyone else? Okay. I assume okay. You want me to explain again? Fine. So I suppose you want the explanation for how are we estimating lambda, or uh, okay. I suppose it's the lambda part. So you see in the expression of the log likelihood, it's minus lambda plus k log lambda minus log k factorial. K we know because k is my observation. It's the lambda which I would like to explain. So lambda is the what you expect in that bin, right? It's what is the expectation. So you know that this distribution is going to follow an exponential because this is what you're trying to fit. So exponential, let's say I'm considering this bin. Okay. So the value of exponential, because it's a normalized PDF, the value of exponential at time t is given by 1 by tau. Tau is the parameter that you are trying to determine, minus e to the power ti by tau. Ti is this mid value. Then let's say this is the fraction of events in this bin. Okay. But if let's say you got n number of events in this whole histogram, so you multiply it by n to get the number of events at this time interval, right? But you still haven't got the number of events in this bin. Now, I'll zoom it here. So you assume that the exponential is not varying too much in this bin. I have exaggerated. It seems like varying. Let's assume that the bins are thin enough that the exponential really doesn't vary appreciably, which means that the number of events is at this time interval is the same as the number of events at the other time intervals, right? So it's just number of events in this bin will be just multiplied by the bin width. Can we just do a CDF up minus CDF down times total sample size to get the expected values within that bin? You want to use cumulative distribution functions. CDF up, what is CDF up? Can you please say? Sorry, I didn't get it. I just know that that's cumulative distribution function, but what is up and down? Upper limit of the bin and lower limit of the bin. But you mean to get the total sample size to get the expected, but that way you're not involving the exponential anywhere, are you? I mean, no, integral. So that will give you the observed number of events. in that bin. What you are, I think what you are saying is just take the integral in that bin, right? That's what you mean. If you're taking integral in that bin, that's giving you the observation. That's the observed number of events. What we are trying to determine is the expectation. Yeah. I think you can do that as well. Exactly. You're trying to determine the integral of the PDF within that bin. That should also work. Exactly. I see what you're saying, CDF up minus CDF down. Yes, exactly. You can do that way also. And I would say, since you have done this exercise before last year, it will be better if you can do this way. Okay. Okay. So now we have, exactly, that way you will not need to know TI. I completely agree. I would suggest that you try this way, what you are saying. So, now that we have all the ingredients with us, so the first thing would be, I suppose this last point was clear to everyone now. Okay. So what you have to do is now, in order to code, I will provide you the code which has 5,000 random variables exponentially distributed, stored in a root file, and also histogrammed. So what you have to do is just to write a log likelihood function. So you know the expression of the log likelihood function for this is the expression for the log likelihood function. Okay. And you just have to estimate the lambda parameter. Okay, you already know. Once you have and sum it over all the bins, because it's sum over all the bins. So once you have summed over all the bins, provide it to Minui, and Minui will give you an output. Okay, that's it. I'll provide you the link to the code, and before that, let me also share my code. Actually, I'll just show what baseline I have. Let me just quit sharing from here. So I'll just provide this partially written code. Tau truth is 5, and this you will need when you do the second part of this exercise, that is looping, and step size is this. And this you will need, this will be just generating 5,000 random variables in one experiment, and in the last part of exercise, this variable will be needed. So here it's just generating 5,000 values of random variables following exponential distribution with the tau parameter that you provide. This is just filling the tau parameter, all the random variables in a tree, and this is a small function that can just plot the histogram. Uh, okay, so I'm just creating one output root file and providing the tau truth which is 5 here, and then you're generating 5,000 random variables of time measurements, calling this function, and then fill tree with time. Just this created a root file, and then this is just histogramming. Then, so this is the function where you have to start coding. So here you are saying write the bin fit time measurement. You define a function FCN, which takes the tau parameter because this is to be fitted. So here you loop over all the number of bins, and this is the place where you have to code for log likelihood. Once you have written the log likelihood, you return that log likelihood minus 2 log L is F, and then you call menu. So this part I have already done for you. You just have to write here. Okay, I'll provide the link to this code. Any questions till this point?
Shilpi, why did you use the root file? This was for what?
Just for easy, I mean, just storing. One may not use actually. Just storing the random variables, because when we do, yeah, I think there is no need to store in the root file. So the the exercise is, it is meon lifetime measurements underscore bind dot notebook. This is the code that you have to use. Is it clear to everyone, or are there any questions? Okay, just raise your hands if you have any questions. I'll give you like, let's say 20 minutes to code this. I think we'll have to carry over the second exercise to tomorrow. Is everyone following the exercise? Okay, great. Don't hesitate to share if anyone has completed writing that log likelihood term. Has anyone managed to do this? Would anyone like to share the notebook? I can stop sharing the screen. I hope people are progressing and not stuck anywhere.
Maybe by name you want to ask someone the status.
Okay, I'll throw a dice and I'll see whose name comes up. Prajita, do you want to say something? Are people still doing the exercise or I do not know? Okay. Do you want to share your, okay, you're writing it here. Just a second. Why are you having to take the CDF? I hope it's doing the right thing because you just need to integrate over the function from one bin edge to the other bin edge. But it okay, it should give the same thing, I believe. Yeah, it should give the same thing. Expected counts is enter times probability. Okay, that seems right, but you haven't shown. No, 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 no. Log likelihood is the sum of all the bin counts. That doesn't seem right. This doesn't seem right. What you have written here. Okay, sorry, it was a truncated line. Sorry. Into log of expected counts minus expected counts. Okay, seems right. So then can you see what kind of fitted parameter that you get and also the uncertainty on that? What error is coming? What error do you see? Okay, that you have to sort out. How about everyone else? Deepak, are you able to write the term? But could you write the log likelihood term? Okay, I think I will check after 10 minutes. How is it going? Can you share your screen maybe? I'll stop sharing. Can you scroll a little down? Okay, but what is f? You haven't assigned, so this function is returning f. F should be equal to minus 2 log L. So yeah, you just have to assign the value of f. I think that's the problem you're facing. You got it? So your FCN is returning some a variable called f, but f is not assigned any value. So f should be equal to, at the end of summing over all the bins, your f outside the loop of for loop, it should be f is equal to minus 2 log L. But that should be outside like the for loop before return f. Yeah, exactly. So you can try with that and let us know. Anyone else? How many you have been able to write the log likelihood term? Can you please raise your hands? Okay, so did you compare with your truth parameter tau? What values do you get? Can you also write what values do you get? Okay. No, but you're not integrating it. It should be integrating, like using CDF would be the right approach, Deepak, because uh, you're just subtracting the values at two ends. It's not integrating. And then in log L, there are two terms. Bin counts into log of lambda and minus lambda. So it's not just a probability; it's the number of events. So you have to convert these number of events. So it will be the integral. Actually, integral will give you the number of events. So whoever has raised their hands, can you tell what value did you get of the tau parameter? Okay, great. So whoever has done this exercise, you can move on to the next part of the exercise, and that was, let me check. That was now loop over the tau parameter within a certain range. The range that I had considered was 5 minus zero point 0.8 and 5 plus zero point 0.8. So the low range was 5 minus zero point 0.8 and the high upper range was 5 plus zero point 0.8. So loop over in with a step size of 0.01. So just calculate the minus 2 log L for each value of such loop parameter, and plot it as a function of that looped parameter. So minus 2 log L as a function of tau, plot that and see what kind of shape you get. Okay. So essentially this part of the exercise I'm saying. So here compare the minima with what Minui gave you and compare this uncertainty band with what Minui gave you. Whoever has completed this, please move on to the second part. Yes, everyone is getting slightly different. That also seems all right. They are getting different values because you're generating differently. The random numbers, depending on what seed you are using, you get different values of those 500 random variables, 5,000 random variables. I hope many of you have moved to this graphical exercise method. So how many of you have moved to exercise, meaning the second part of the exercise? Can you raise your hands? Good. That's it. No one else? Are people still there? Okay. I'm hearing, I think only from like 4 or 5 people. Can others also comment or say, have they been able to solve, have they been able to code the log likelihood? It will be great to hear. I mean, the purpose of the tutorial is just, I could have moved forward. I'm waiting so that you have time to understand and see how it is being done. So it will be great if you can tell me whether you are stuck in something or uh, you have been able to move forward. Any feedback will really be very useful. Otherwise, I'll just say names. I mean, I'll just call you. And Mitali, have you been able to do this? I'm not sure if people are really listening to me or not. Okay. Yes, don't be shy in it. You can at least type that confirms that you're following. Make use of the this tutorial time as much as you can. But it is still not integrating, right, Deepak? As someone rightly pointed out, it's the CDF, not this. Do we have to do minimization by defining the derivative and all, or do we? So for the minimization, you can just pass it on to Minui. That's for the first exercise. But in the yeah, exactly. CDF is there in SciPy. So uh, so then so for B part, no, you don't have to do the minimization. So you just plot -2 log L as a function of this tau parameter. So for you loop over the tau parameter, for each value calculate -2 log L, and then just put that in an array. So for each value of the tau parameter, just plot what is log L. So on the y-axis comes -2 log L, on the x-axis comes the tau parameter. Okay, so then the minima, what is the derivative doing? It's just giving you the minima, right? So just look where the minima is. That's your best fitted parameter. So this is just a very simple-minded approach without using any derivative to see graphically exactly how to extract the best fitted value, because log L for the best fitted parameter, it's the log L which should be maximized, but it's minus log L that should be minimized. So it's easier to see then. Yes, Deepak, you will have to use Minui for the first exercise, for the first part of the exercise. For the second part, you can just loop over. I mean, this is just getting a feel of what Minui is doing essentially. So you are essentially doing what Minui is doing, but Minui is doing using smarter ways to get to choose the tau values, because we know what the true value is. So we are just looping over in a small window just to understand how Minui is doing. Okay.
So Shilpi, should we continue like this or should we give them?
I think they can do this. Yeah, they can do this at their leisure today, whenever they can. And then tomorrow, can we start a little later because I think it's only today's exercise that we will do.
Uh-huh.
Plus, whatever doubts or questions they had, and I think they had something from day one. So I'll just repeat the exercises from day one. That's it.
But there will be a lecture by Arun also, right?
No, Arun said that that's it.
That's it. Okay, so that's perfectly
Yeah,
fine.
no, I have no further
Can we start a little
on
late
this
then?
topic. But if you want to use some different avenues, they have
No,
some.
no. So let's not start a new topic. Yeah. That's perfectly fine. So let's. So what time you would like to start tomorrow? Shilpi?
Maybe 10:30.
That
Ten
that
thirty is fine because so let's say in half an hour to 45 minutes I'll do this exercise which is remaining from today.